Hello, Internet. We are live.
MLSys seminar series. I'm Karan. We have with us today Dan, Piero, Fiodar, and our guest today, Carole-Jean Wu from Facebook AI. As always, we're going to have a 30-minute talk by Carole, followed by a 30-minute podcast-style discussion where you can ask questions in the live chat. Feel free to send in questions during Carole's talk as well, and we'll keep track of those questions. Today is also our 24th episode, which is technically 25 since we're computer scientists, so a quarter century old in terms of the seminar series. So thanks for sticking with us if you've been watching since the beginning. And if you're just joining along, please subscribe and subscribe to our mailing list and YouTube channel and keep following. A little bit about Carole. Carole is a technical lead and manager at Facebook AI Research. She works on designing machine learning systems for execution at scale, which includes personalized recommender systems and also mobile deployment. She chairs the MLPerf recommendation benchmark advisory board and has co-chaired MLPerf inference and serves also on the ML Commons board as director. She got her PhD from Princeton, and she has received a ton of awards and a few best papers as well. So a very long and very interesting and storied career there. We're very excited to have you, Carole, and please take it away. If you can, I think your screen sharing is working, so feel free to start whenever you're ready.
Hey, thanks so much for the invitation and introduction, Karan. Hi, everyone. It's a great honor to be here at Stanford's MLSys seminar. My research at Facebook, as what Karan has introduced, focuses in the intersection between systems and machine learning. Today, I'm going to tell you a little bit about my experience designing AI systems for recommender models and beyond, share with you some of the future directions in this field. So today, in particular, I want to draw your attention to an underinvested but very important area of deep learning. And this is about neural recommendation and ranking systems. Personalized recommendation is the task to recommend content such as books to users by predicting the likelihood of user interest on the particular items. It is one of the most important deep learning workloads supporting a variety of products within Facebook and across the entire industry. In addition, these recommendation algorithms actually underpin many different application domains, from the search engine to e-commerce platforms, and from personalized healthcare to chip design and weather predictions. Among all workloads trained with the machine learning execution pipeline at Facebook, personalized recommendation is by far one of the most important and fastest growing workloads at Facebook. Among the total AI training cycles, about 50% is devoted to recommendation models. And for AI inference, that's about 80%, with the remaining 20% of the cycle devoted to non-recommender use cases, covering computer vision or natural language tasks. Meanwhile, if you take a look at what the system research community is looking at designing systems for, things can look quite different. So here is the pie chart that shows the paper published in top-tier system conferences between 2014 to 2019. What we found is that the majority of system researchers were focusing on building and optimizing systems for neural networks that deal with vision or language speech translation. Only 2% of the paper studies recommender systems. And before we uncover the underlying reasons, let's first take a look at how recommender systems work. From a very high level, the recommendation pipeline involves two major phases. First is to retrieve a large collection of potentially interesting content, followed by a ranking stage. So what that means is that we start with hundreds of thousands of candidate items at the information retrieval stage, and across the different stages of the recommendation pipeline, increasingly compute-intensive neural network models are used to produce more accurate content recommendations. And then we come up with a ranked list of items. And so for Facebook, this means that ranking hundreds of thousands of items with large-scale models with billions to trillions of parameters in order to serve billions of users worldwide. So how does this neural recommender systems work? Recommendation models typically have two types of inputs. First is the continuous inputs that are processed by a set of DNN layers. These are often implemented as fully connected MLP layers. And the common continuous input features can include, for example, time of the day that's often expressed as continuous variables. The second type of inputs are categorical input features that are often represented as multi-hot encoded vectors. For example, the entries in a sparse vector can represent books a user has searched or categories of items that the user has liked. So given the scale of internet services that use recommendation models, these vectors are not only large, but can also be very sparse. And so one way to transform these sparse inputs into dense representation is to use embedding tables. Entries of the multi-hot encoded vectors are used to index into rows within the embedding tables to read low-dimensional embedding vectors. And these vectors are then pulled together to allow interactions between the learned information and combine with the output of the dense DNN stack. Finally, a predictor DNN stack will output the probability of user interacting with the particular items. So for example, given a user and book pair, the neural recommendation model is used to predict the likelihood for the user preference on the book. And if we were looking at the system resource requirements for different portions of the recommendation model, the dense DNN stack implemented as multi-layer perceptrons are compute intensive, whereas the operation on the embedding tables is memory capacity and bandwidth intensive in terms of memory storage and the memory bandwidth consumption. So now when it comes to evaluating how effective systems are for training and serving recommendation models, it is intuitive that ranking more items is going to lead to better recommendation quality. And therefore, from systems perspective, what we want to focus on is to maximize system throughput. And at the same time, there's a user at the other end waiting for the rank recommendation list. And therefore, we also have a very firm latency target to meet in order to maintain high quality user experience. And finally, from the system design and optimizations perspective, we have a latency bounded throughput optimization problem to solve here. Given the importance of recommendation and ranking use cases, next we'll take a look at what unique system challenges we face when building systems for this class of deep learning workloads. I will then talk about our recent works to design and optimize systems for deep learning recommendation models. And before concluding my talk, I'll also talk about several work in progress and important future directions. And here are a few papers related to different parts of my talk in case you want to have a deeper dive into the individual topics. Okay, so first, let's take a closer look at what system design challenges for training and serving deep learning recommendation models. I want to highlight 3 unique characteristics. First is the large embedding tables. Deep learning recommendation systems demand far more memory resources than other type of neural networks that we are used to. Second is model heterogeneity across network architectures. Depending on the specific configuration of recommendation models, the models themselves can have a variety of features. For example, the configuration of the MLP layers, the size and dimension of the embedding tables, and some of the more advanced recommendation models today have attention layers in order to better capture the temporal information in the data set. And finally, performance variance can also introduce interesting design challenges. When these recommendation models are deployed in the production environment, what we observe is non-negligible performance variance that can come from at-scale execution, such as recommendation query arrival characteristics or model collocation. And depending on the specific execution style, recommendation inference can face different degrees of queuing delay or interference. So what does the resource requirement characteristics of these embedding tables look like? Compared with neural networks that we are familiar with, such as CNN, fully connected layer, or RNNs, recommendation embedding tables introduce unique system optimization challenge from the storage capacities aspect. The storage requirements is order of magnitude larger as compared to other neural networks. In addition, the compute intensity is much lower as compared to CNN FCs. And the sparse vector lookup to the embedding table produce irregular memory accesses. These embedding table operation can introduce memory access patterns that has poor locality at the CPU or depending on what processor, the cache hierarchy, memory hierarchy of the processor. And what this means is that it can introduce significant stress on the existing off-chip memory bandwidth. And I see this as an area that can, where a lot of innovation and specialized memory optimization solution can appear. The second challenge faced by recommender system is model heterogeneity. At a high level, we can generalize the collection of recommendation model at Facebook into three major categories. Models in each category can demonstrate varying parameter specifications as described in the table. And in aggregate, they are about 200 different recommendation models running concurrently at Facebook's data center fleets. Across the board, when examining recommendation use cases across the entire industry, we find three distinct architectures. First is the embedding-dominated models with many large embedding tables and many parallel embedding vector lookup operations. And there is also the MLP-dominated model with deep and wide MLP layers. This class of model can also implement many output DNN stack. And finally, there is the attention-dominated recommendation model that can introduce attention modeling techniques to capture more complex feature interactions. And because of the diversity in the memory and compute requirements, system optimization for deep learning recommendation models can be quite complex and challenging. One system size won't optimize for all. Next, let's take a look at the performance optimization opportunity when we start considering at-scale runtime execution effect at the data center level. Imagine a hyperscale data center with some level of system heterogeneity, CPU, GPU, or AI accelerators of your favorite type that is used to serve web queries, where recommendation models are used to produce more relevant search results or newsfeed. Queries with hundreds to thousands of candidate items can come into the recommendation model pipeline for ranking. A few output candidate items are then presented to the users. Here, there are two important runtime effects concerning the execution time performance of recommendation inference: the real-time query arrival characteristics and the query working set sizes. The query working set sizes here refers to the number of user item pairs in a recommendation request. So here we profile the production recommendation pipeline and find the following query size distribution pattern. And here the y-axis is showing the histogram, the frequency of the different query sizes. The varying query size distribution exposes interesting system design challenges and opportunities. So for example, the long and heavy tail expose performance acceleration opportunity with computation offloading onto the AI accelerators. And the non-uniform query size distribution is what led to our recent ESCA 2020 work called diffraxis. In order to study this recommendation inference program end-to-end, we first built an infrastructure called diffraxis. Diffraxis basically implements this cross-stack system components in order to emulate real-time recommendation query serving. The infrastructure has this front end that generates recommendation queries of different sizes, and the sizes of the query follows the production observed distribution that I showed you previously. The front-end query generator then sends the recommendation queries to the runtime scheduler, following the commonly observed Poisson distributed arrival pattern. And then the Rexis scheduler will forward the queries to services that can implement different recommendation algorithms. Depending on the specific use cases, these different type of models can then be run on CPUs or any available AI accelerators in the data center setting. So now, how do we determine the query parallelization and offloading strategy given the specific inference system architectures then? In order to optimize the tail latency bounded throughput performance for at-scale recommendation inference, we propose a scheduler that takes into account four major hardware-software system aspects, including the recommendation model architectures, the underlying system architectures, the various runtime effects, such as the query arrival rates and the working set sizes of the request, and the latency targets specific to the use cases. Our proposed scheduler is called DeepRecSched. DeepRecSched is built on top of a simple hill climbing search algorithm to determine the optimal query size and offloading threshold for the various recommendation service. And here we implement DeepRecSys on real system and show that the proposed scheduler can double the throughput performance of the underlying service. If we have an additional AI accelerator, such as GPU, we can further increase the latency bounded throughput by 5 times more. When we start considering energy efficient execution scenario, we'll quickly find out that the optimal energy efficient execution platform is going to switch, and that is determined based on the specific model architecture and also the power performance profile of the serving system. So that's about DeepRecSys. I won't have too much time to go into detail, but please go to the paper to learn more about the nuances of this work. Recall the 3 key system challenges faced in deep learning recommendation systems. DeepRecSys tackles 2 of the 3 aforementioned system challenges faced by industry scale recommendation models, namely model heterogeneity and performance variance. What are we doing to address the embedding table challenges then? Let me highlight some of our recent works in this space, covering both inference and for training in the next couple of slides. We have a recent work also published at ESCA 2020 called RecNNP. In this work, we examine a near memory processing solution to perform embedding vector gather and reduction operation within the DRAM module. And remember, this is because these embedding tables introduce high memory bandwidth demand. And so it actually makes quite a lot of sense to perform the embedding operations directly in the DRAM itself. So to tailor the near memory processing solution for production scale recommendation inference, we complement the baseline design with 3 architectural optimization techniques, including the memory side caching, table-aware packet scheduling, and hot entry profiling. And we take the proposed design with simulation-based evaluation and show that RecNNP can speed up the memory latency by up to 9 times over a highly optimized baseline. We also consider the inference performance improvement for end-to-end recommendation inference in the work. What about recommendation model training then? What system challenges do we face when training deep learning recommender systems at scale? Recall that the major components in state-of-the-art deep learning recommendation model include the dense and MLP layers and the embedding tables. So when we train these recommendation models, we will map the dense part of the model to trainer servers, while the sparse embedding tables are mapped to the parameter servers. So here, the large embedding tables, often in the sizes of gigabyte to terabyte, can introduce optimization opportunities at the training time. So for example, depending on the training system specification, there are different strategies to map or shard these embedding tables onto different types of memories on the training system. Embedding table can be placed on accelerator device, on the host memory, on the remote memory partition, or some combinations across different memory types. Our recent HPCA 2021 paper analyzes the embedding table placement strategies across different training systems in production. And what's interesting here is this is actually the first time detailed embedding characterization result on industry scale recommendation model is presented, where we talk about all the nuances to enable system support in order to train recommendation model on GPUs. And depending on the model architecture, the embedding placement strategies can vary in order to achieve optimal training efficiency. As recommendation models grow in size into multiple terabytes, it calls for novel algorithms and system solutions in order to achieve better performance and efficiency scaling across the entire system and infrastructure stack. We must consider compute, networking, and storage components all together in order to optimize the machine learning training pipelines end to end. In addition, our EastPass 2021 paper presents the scalability challenge and scale-out solution studies for recommendation inference. Okay. Now, in order to enable next generation complex recommendation models, we are also looking at algorithmic approaches to tackle the memory capacity challenges from the embedding tables. In this year's MLSys conference, we presented a customized tensor train compression mechanisms to trade off embedding large memory requirements with computation. Our proposed design is called TT-REC. TT-REC replaces the large embedding tables with a sequence of low-rank matrix multiplication. And this is an appealing solution space because the on-chip memory capacity of AI accelerators is quite limited, but computation is nearly free. And so in order to mitigate the training time overhead that can come from the additional tensor train multiplication, we propose to add a software cache in order to capture the embedding vectors of higher access locality. And by doing so, we can eliminate the additional computation required for the frequently accessed recommendation embedding vectors. Here, we evaluated TT-REC on 2 open source recommendation data set and show that we can achieve roughly 100 times reduction in the memory capacity requirements while only increasing the training time by 10 to 20%. And that training time can be mitigated by the TT cache that we introduced. And all of that comes with negligible model quality trade-off. Finally, given the particularly long training time for recommendation systems, often in the order of days to a few weeks, it is critical to have failure-tolerant, reliable infrastructure for model training. So in our other MLSys 2021 paper, we take a data-driven approach to quantify the reliability cost for recommendation training workflow. Here, we show that the reliability overhead of a checkpointing-based training system, the reliability overhead here is heavily coupled with the specific failure pattern, resource availability, and other concurrently running training workflows. And all the combinations make determining the optimal checkpoint period challenging at scale. So to improve the training efficiency and reliability at the same time, we came up with a partial recovery training system solution called CPR. First, we proposed a metric for machine learning model developers to control the amount of training samples that can be lost during the training process without affecting model convergence. This is a key contribution as for the first time, a metric that correlates well with model accuracy is empirically identified. We then use the metric to modulate the frequency of the checkpoints. In the paper, we show that CPR can reduce the reliability overhead by over 90% without notable accuracy degradation. Okay, so let's get back to my earlier points on the underinvestments of recommendation system research. Why is everyone writing research papers about vision and natural language processing when we have a fairly important problem in the deep learning space at our hand on how to design systems for recommendation model training and deployment? If you look at the computer vision and NLP domains, they are standard workloads and data set that researchers have agreed upon to evaluate new research ideas. This wasn't available for researchers and system designers to study recommender problem. And this is why I'm really excited about DORM. DORM is Facebook's deep learning recommendation model that was open source about 2 years ago. DORM can be configured easily to study specific model architectures that you care about. For example, the width and depth of the dense CNN stack can be varied, and the number and sizes of the embedding table can also be tuned to match features found in a data set. And to study the effect of model heterogeneity, we also created a collection of 8 industry representative recommendation model architecture by expanding beyond Facebook's DORM. This is a collaborative project we have with Professor Brooks and Wei at Harvard University. We built this experimental infrastructure that enables us to study system design and optimization strategies for a variety of recommendation models running on a variety of systems. We also made the code available in case you are interested in using it for studying your favorite system optimization technique. So on top of the DLRM and DeepRexes, there is also an industry-wide effort to develop a machine learning performance benchmark suite, and this is MLPerf. I was with MLPerf since 2018. Initially, as the MLPerf inference co-chair, it was immediately obvious that MLPerf needed a representative recommendation workload in the benchmark suite. Today, the MLPerf benchmark suite includes the DLRM benchmark with the open source click-through rate dataset from Pretio AI Lab. So hopefully throughout this talk, I've convinced you that recommendation models are important. More than 80% of Facebook's AI inference cycle is coming from recommendation use cases. But in 2019, only 2% of the paper in our system community is looking at this application domain. I also talk about a set of unique system challenges faced by recommendation models and share with you some of our recent works going on in this space. And in order to enable more research into the space, we also created new infrastructure and have standardized the benchmark and data set for our community to leverage and to build more high performance, efficient, and reliable systems for neural recommendations together. Now, in this very last part of my talk, I want to touch upon a few directions that are important for us to pay attention to for the powerful AI technologies that we are developing. They are three system design aspects that I'm deeply interested in and care about. First is to enable high performance, efficient AI systems for deep learning models that can provide better interpretability. One of the biggest challenges faced by deep learning models is the ability to explain the prediction outcomes. Understanding AI systems is important to ensure that models are actually working as intended. And we are still at the very early stage of understanding how these neural networks work. So from systems perspective, we are interested in enabling recommender system modeling techniques that can provide better content representation and interpretation. And therefore, the model can produce more interpretable outcomes using techniques such as graph neural networks. Can we design faster machine learning systems and hardware in order to enable more efficient execution for such modeling technique? On the privacy front, training model with sensitive data needs privacy-preserving safeguards. One of the important opportunities for system architects is to develop system support to enable more on-device AI. Neural networks today running at the edge are a lot smaller and a lot more efficient. But at the same time, more and more neural accelerators are also making their ways into edge system. And this is actually a tough problem from system optimization's perspective. As what we show in the HPCA 2019 paper, one of the key system challenges enabling on-device AI is the highly fragmented ecosystem of mobile SoCs. In total, there are over 2,000 different types of SoCs in the mobile space. There's no standard mobile SoCs that we can optimize our machine learning kernel for. I believe this is where automated compilation, runtime strategies are going to shine, and a lot more work should happen in order to accelerate the enablement of on-device learning. So what's the implication of system heterogeneity on enabling privacy-preserving secure AI solutions then? Federated learning is a great starting point. It supports training neural networks across multiple decentralized edge systems holding data samples locally. How do we actually make the style of distributed training approaches more robust and more efficient for edge applications, while also taking into account user mobility, data heterogeneity, and system heterogeneity that we talk about? In addition to the training side of things for on-device machine learning, edge inference optimization is also important. As the 5G technologies start shortening the distance between edge and the cloud, the much higher communication bandwidth capacity with 5G gives rise to a new research challenge, and that is deciding when machine learning inference should run at where, which devices. Intelligence services today can choose to run between the CPUs or any coprocessors that sits on the same device, or exploiting connected systems such as the cloud or a nearby locally connected systems that could be more powerful than the wearable devices itself. By doing so, the service can now scale out the performance and increase the energy efficiency of edge mobile devices. Our recent work proposes autoscale that customizes a reinforcement learning-based model to accurately predict the optimal execution platform while adapting to the stochastic edge cloud collaborative execution environment. So now, with the increasingly better system support for the edge cloud execution environment, it is quite exciting to see on-device learning that weren't previously feasible to start happening more and to enable more data privacy for machine learning execution. In addition to enable more on-device learning, I want to bring up the impact of AI on our environment to your attention. And that's on sustainability of AI computing. Over the previous 1 year span, from 2019 to 2020, we witnessed an 8-fold increase in the amount of computation required for machine learning model training at Facebook. Similarly, the number of parameters in state-of-the-art language model have increased exponentially, currently at over 1 trillion parameters. The amount of computation required to train state-of-the-art DNNs is increasing in a very unsustainable pace. And so now, if you look at the amount of carbon emission produced by model training, it's dire. At this year's Micro 2020, Dr. Bobby Matei delivered a very inspiring keynote on what we computer system designers can do in order to architect a sustainable planet together. And Professor Natalie Enright-Jurger followed up with a SIG-ARC blog post on the sustainability benefit of composable hardware design, such as chiplet-based systems. Our community is starting to pay more attention to designing greener systems. I want to take this opportunity to highlight our recent work that takes a holistic approach to understanding the environmental impact of computing end-to-end. This is a collaborative work carried out by colleagues at FAIR, Facebook's sustainability team, researchers from Harvard and Arizona State. Here, we take a data-driven approach to understand the carbon emission breakdown for computing. In particular, we perform an analysis called hardware lifecycle analysis, a very commonly used methodology to analyze the carbon emission across product lifecycle. So here, we analyze the publicly available sustainability data for Apple's mobile device, and it turns out that the manufacturing carbon emission dominates the overall carbon footprints of Apple devices. However, when considering the carbon footprint of computer systems, system architects often focus on reducing the product use or operational energy consumption. The manufacturing or the embodied carbon cost of systems is the elephant in the room that very few talk about when discussing computing's environmental impact. What about the cloud? Similar story. The operational power consumption of public cloud today is quite optimized, thanks to all the efforts going into optimizing the data center PUE, server power efficiency in the past 2 decades. And with more available and better access to renewable energy capacities, manufacturing of system and hardware becomes the dominating source of computing's carbon emission. A lot more detailed analysis is presented in this HPCA 2021 paper. Check it out. So given the growing demands of AI use cases, making AI systems run faster, more efficiently, and more reliably is an important dimension to reduce environmental footprint of AI computing. I share some of the works in this space with you today, but there is a lot more to be done in order to achieve an environmentally sustainable future for AI. For example, to amortize the upfront embodied carbon cost we pay to get the AI accelerators into the data center, we should ask the question, how well utilized are these accelerators for systems lifecycle? Lots of AI model training experiments end up not utilizing the parallelisms provided by the hardware very well. We see a significant portion of training experiments utilizing GPUs at 30 to 50% only. One way to improve the training accelerator utilization is to innovate in the algorithm space using techniques such as tensor train compression, which I talked about in earlier part of my talk, or come up with model architecture such as transformer that can better leverage the hardware parallelism. We also have much more data for AI training these days, but what is the optimal set of data for specific machine learning tasks that we are interested in? How do we enable smooth edge and cloud collaborative computation in order to reduce the resource redundancy and improve infrastructure efficiency end-to-end? Taking a step further, how does the dominating source of embodied carbon cost from manufacturing of hardware influence the next generation domain-specific cloud that we are going to build? If we were designing training infrastructures from the ground up, how will we take into account system modularity, reliability, performance per watt efficiency on top of the performance requirements of these domain-specific workloads? How do we achieve acceleration efficiency by taking into account the upfront embodied carbon cost? We also need the tools to help us quantify the carbon footprint of AI to measure computing's impact on our environment in a data-driven manner. We need a metrics that help us to make quantitative comparison between different system design and optimization approaches. And finally, the role of renewable energy brings in interesting optimization challenges and opportunities. For example, efficiency and availability of renewable energy can have very different time-varying intermittent nature over time, over the day, or across different geographic regions. So quite a lot of dimensions to take into account in order to build environmentally responsible AI systems going forward. In this talk, I share with you some of the exciting work that we are carrying out at FAIR in order to build systems for deep learning recommender systems and how to enable system support for deep learning models that can provide more interpretable prediction outcomes for more on-device learning and to achieve more environmentally sustainable AI computing going forward. The work I'm very fortunate to share with you today is carried out by many colleagues and collaborators at Facebook and from the academic communities. To take this moment to thank all the collaborators to carry out these exciting projects together. And finally, thanks so much for your attention. Come and work with on some of these very exciting topics that you may find interesting in pursuing together. Thank you.
Thanks so much, Carol. Great talk. We covered a ton of ground. So I think all of us also have a bunch of questions, as well as folks in the audience had some questions coming in. If you're in the audience, feel free to post your questions in the live chat, and we'll try to get those across to Carol. So I just want to kick things off by maybe asking a question about recommendation systems and Facebook. It's maybe a complicated history in some sense, because both Google and Facebook have got a lot of heat for designing systems that potentially, lead to radicalization, or even like cases where, they kind of spiral out of control for particular users. And I'm curious if you've observed that behavior, and if you have comments on, internally what Facebook might be doing to fix that. And I know it's a hard issue in general because, the design of these systems is not necessarily well understood yet, but just curious about what you might be doing to fix that.
Great question, and thanks for asking it. I think this is a very important questions that we ask ourselves. Debate about those questions on what I can do from system as a system architect. And I think there's a lot of work and interesting directions that we are looking at. I don't know if people are aware of this fairness flow tool that FAIR has recently shared with the community. I think having the tools and metrics to help us evaluate the fairness aspect of machine learning model is a very important first step. And that's going to give us the tool to quantify fairness and bias in various parts of machine learning models or in the data set. And from the system optimizations perspective, I found it quite interesting in the sense that for a very long time, system architects may not care about all these algorithm properties. We sort of come up with the high performance systems, we optimize for energy efficiency, we optimize for low latency and all of that. But there's very little knowledge about what does these system optimization techniques that we put into the hardware, how they influence the results of machine learning prediction. So let me give an example. We can come up with the latest quantization mechanisms. We can come up with the latest weight pruning techniques, right? But how does these techniques actually influence the fairness aspect of model prediction? I don't think this is something that system designers know very much about and actually do the due diligence to evaluate the effect on fairness bias aspect of variety of different machine learning use cases. And I think there is definitely a lot more work that needs to happen. And this is something that we are also actively working on.
Awesome. Thanks for your answer.
Actually, Carol, I think I have a question that is, to a certain extent, potentially a little bit of a follow-up to this, which is also diving deeper into what you were talking about regarding the fact that the amount of research that goes into recommender system opposed to other topics. One aspect, in my opinion, that could be really important there is the fact that for doing research in recommender systems, you also need to run user studies, and those user studies require an infrastructure and running things live with people, and so that, in my opinion, makes things more difficult. And I'm curious, what is your take on that? And if that could be one of the reasons why there's less research on that, and also why some of the more dynamic system aspects of the interaction between systems and users are a little bit neglected, and we discovered that the side effects of these dynamics only later on.
Very good question. I guess maybe I can clarify a little bit what I meant by recommender system research is underinvested for this machine learning workloads. I think there is a lot of happening in the algorithm side of things. There is this conference that's devoted to just recommendation algorithms and all of that. And there's tons of exciting work going on to look at various aspects of recommendation algorithm, like fairness bias, quality, algorithm innovations. But however, I do see a gap between the system community designing the latest and best hardware in order to provide more efficient execution for recommendation models. And this is true for both training and inference systems. And I think that's the gap that we can help fill from system architects' perspective. And really, it requires people to work in the intersection between systems and machine learning.
Yeah, that makes total sense. Yeah, I agree. And do you think that the human in the loop aspect is something that, from the system perspective, particularly important, or do you think that that's just more on an algorithmic aspect that one needs to study?
Yep. So the answer is yes. Human in the loop in the algorithm side of things is an important aspect, and I guess that may be something that from designing systems perspective, I think the feedback can be aggregated into the data set that I use to train the model on the systems that I design, right? And so I hope that all those feedback and information is already annotated in the data set, such that if I need to evaluate certain algorithm properties, that information is in the data set for me to take a look at. Exactly how that influence the system performance, that could be something that that we can look into further. And I would think that some of these will also relate to the inference system optimization that I was talking about. If for any inference system optimization that we deployed, we need to make sure that all the algorithm level properties that's desired and annotated, specified by the algorithm developer, should be guaranteed. the system design optimization should not take away any bits of the properties that we want to enforce.
Thank you very much for your answer.
Hey, Carol, you talked a little bit about in your talk about sort of standardizing some models or some benchmarks for recommender systems. I'm wondering, how do you evaluate a recommender system kind of with a benchmark, and how do you kind of replicate some of the effects that you could see in production? For example, the classic problems like your recommendations change what the users look at, which changes like what they want, and how do you like evaluate what makes a good recommendation and tackle that problem in a research setting?
Yeah. The first question that we should ask is benchmark. What are we benchmarking? Are we benchmarking for model quality, accuracy, or are we benchmarking system performance? And that's a really important question to ask because for SysML, the interaction between systems and machine learning in general. The benchmarks that I was talking about through MLPerf is an industry standard benchmark suite for system to understand and to enable system developers to make fair comparisons across different hardware. So over there, the recommendation model is used as a system benchmark. Okay, so then how we measure the training performance at MLPerf is to measure time to reaching a desirable accuracy target. So the benchmark suite is going to specify the target, and we basically measure the time to accuracy and use that as a metric to represent the performance of the particular system. Okay. Whereas if now I'm talking about if I'm comparing the effectiveness of recommendation algorithms, then I will be more interested in accuracy benchmarking or data set benchmarking. And so over there, the metric that I'll use will be accuracy. And I may not report training time taken to make that comparison. However, I do think that the last point of my talk on environmental sustainability for AI computing, I think the AI community has to start reporting the amount of resource taken to produce the AI innovation describing a paper. And that's going to require model developers, algorithm designers to think about how to evaluate training time, how to evaluate training resources, and how to translate that into power consumption and the corresponding carbon emission for the experiments. Is it worth to spend all these other resources in order to improve accuracy by 0.01%? Right? Like, ask that question.
Right. Yeah. Thanks for the great answer. I also wanted to highlight a question that we got from the audience in our online chat from Shreya Shankar about what's the kind of the interaction that someone who's building one of these recommender systems has with the system itself. If someone is like trying to design the recommender system or notices some problem, what would a data scientist kind of do when they work with recommender systems? What sorts of things do you log throughout the process? Things like that.
Great question. I guess what I did not touch upon during my talk is this front end of the machine learning pipeline on feature engineering. Like, how do you take the data, annotate the data, clean up the data, label the data, and translate that into features that will be used to train recommendation model, right? All of that is sort of at the front end of the pipeline that I didn't talk about, but they do actually take a lot of resources. Data labeling is a resource-intensive process, and data ingestion can often become the system bottleneck when you look at the end-to-end training system pipeline. So how do you get the data that's stored in the storage transform into the features that we're going to use to train a model with? And how do you get those features into your trainer systems such that your training nodes is not just like sitting idle waiting for data to be ingested into the trainer nodes? And so what the kind of work that's being done in the space will be like, in order to scale out the training efficiency for recommendation model, maybe what we should do is to tease apart the data preprocessing part of the pipeline to a disaggregated service. And so then the different portions of the machine learning pipeline can be scaled out more independently.
Well, thanks for your answer, Carol.
Carol, I had a question about the rate at which some of the systems that you build at Facebook are actually updated and change over time. So I was just curious, like you talked a little bit about these giant embedding tables as well as the various models that you use. At what time frequency do you think about changing the actual like parameters of the models or the embeddings themselves? Because as you know, like as time changes, right, things change, and the representation of those things should change as well. So I'm just curious, you know, how does that process happen? And also, how do you think about, you know, adding new architectures? You talked about these 3 different types of architectures that you have: MLP, attention, and embedding based. And how do you think about, you know, making that jump to a new architecture? And because it seems like there's a lot of challenges that come with that.
Yeah, great question. How do you, so I sort of, this reminds me of research to production iteration. And I guess the short answer is that we want it to happen as soon as we can, as fast as possible, because especially for recommendation use cases, the freshness of the data plays a significant role in model quality. And so the faster you can train with the latest information that you have available, the better you want to sort of translate that into model prediction quality, right? And so the desired outcome is that you want to do that as soon as possible. But then when you start factoring in the size of these recommendation models, you will realize quickly that it cannot actually happen in like even in a day granularity. Like these models takes time to tune. There is a large collection of models that large collection of data that these models are trained with. There could be different algorithms that we want to evaluate for deployments. Right? How do you then compare among the all the competing algorithms? How do you determine the best ranked algorithm given the size of the data set that you have developed, right? Figuring out the ranking of all the different recommendation models is a process that we'll have to go through. And then eventually, once the model is trained, these models are large. And so in order to deploy them, if nothing else, you will have to transfer all the model parameters into your production environment, right? And so all of that is going to take time. And so depends on the specific constraints and the size of the data set, this can happen in different cadence.
And just a quick follow-up, do you also think about backwards compatibility in terms of the recommendation system as it's updated, you know, over time? Do you think about, you know, whether it's making different predictions on the same types of inputs, and that kind of thing has changed over time, or do you know, is that something you pay attention to?
Definitely, yeah.
Hey, Carol, we just got a great question in the audience from Mark Zhao about the sustainability aspect of your work. And Mark's question is, how do you reconcile the dependency of ML on accelerators and ASICs and building all those things, which, you know, may drive up the environmental costs of manufacturing versus the potential benefits of, like, you know, a faster ASIC can train faster, run inference faster, and use less energy cost? Yeah,
those are like the important questions that system designers have to ask. Right? There used to be a time of how we think of what do you call accelerator as free, like it will only give you all the benefits, all the efficiency benefit, right? It reduces the operational energy consumption of AI computings. It improves user experience, whatever you name it. But if you think about the iteration of these AI accelerators, if you sort of update them according to Moore's law, or if you have to design the latest AI accelerator to catch up with the evolution of AI algorithms, if the AI algorithm is still changing quickly, and therefore you have to deploy the next generation of ASIC in similar case, then are we amortizing that upfront cost well? And what are we doing to our environment, to our Earth, in order to have that efficiency benefit? It really like makes you think about the trade-off between general purpose processors, coprocessors, accelerators, FPGA, I don't know.
Right.
And
yeah.
how you build data center scale infrastructure, having these different components in them at the same time.
Right. Yeah. It's really interesting. Especially, sometimes you have data centers that are just full of CPUs. How do you compare that to like, the latest and greatest ASIC and things like that?
And another thing I sort of want everybody to think about is also, I bet a lot of us upgrade our smartphones every 2 years. Okay, fine, 3 years, right? Do we have to do that? Right? And if you think about, there's a lot of smartphones today, well, not today. There's a lot of work that actually go into space, but then I don't know actually what is the percentage of users who actually own a modular smartphone. You would think that the reason why I upgrade my smartphone is because I want to get the latest camera sensor. Like, think about why you will upgrade your smartphone. It could be like for these more amazing camera sensors, right? But then if you have modularity built in, you don't need to upgrade your entire phone to get your camera sensor updated.
Right, exactly. Yeah, it's really fascinating. And I think I remember, there were some phones that tried to release some of those a while back. I think we're getting close to the end of the hour. So kind of maybe as a last question, also on the sustainability angle, I'm curious, from your perspective, are there any things that are kind of specific to recommender systems and recommender systems workloads about kind of how you would design or co-design hardware for sustainability, perhaps, compared to, computer vision or NLP or various other use cases?
Cool. Interesting question. And I think maybe this can be decoupled from recommender system. But okay, so I guess the rule of thumb is that tagging onto what I was talking about, I think we should think hard about the composition of different type of hardware that we may put into a system. So let it be the CPUs, there could be accelerator components, and how do you actually integrate these different components together? I mentioned about the chiplet-based architecture. Various different GPUs are adopting chiplet systems, architectures, CPUs is doing that. I think AMD has the chiplet CPUs now. And now, like, what does that mean to the next generation AI systems design, right? So that's what. If you look into recommender systems and sustainability, you could also use recommendation algorithms to do some of the fancy scheduling of workloads. So you could schedule compute to data centers where there is more renewable energy for that time of the day in that particular geographic regions. And so machine learning algorithms can be used to improve this part of AI computing as well. It's like machine learning for systems for machine learning.
Awesome. Thanks so much, Carol, for taking all these questions and spending time with us to walk over some of the work that you've been doing, which is really kind of amazing how vast the body of work is. Thanks so much also to our audience for tuning in this week. As always, we'll be back next week with Guanhua Wang talking about disruptive research and distributed machine learning systems. If you haven't already, please subscribe to our channel and subscribe to our mailing list. We send out weekly emails about speakers, and we don't spam your inbox at all beyond that. So thanks so much for joining in, and bye-bye.